We are here from Allen High School, and welcome back to your next video, my best chem students from Allen High School. You are all amazing. We're working on atomic structure and theory, and we were going to discuss Schrodinger. Now, Schrodinger came up with, now called Schrodinger's equation, and there's this book that he wrote called Schrodinger's cat and all this about uncertainties. We're not going to get too much into this. If you'll notice, this is a triple integral. There was actually a day when I could, this is supposed to be me, right? There was a day when I could solve Schrodinger's equation for a hydrogen atom or maybe a helium ion. I don't know that I could do that anymore. But he took this complicated equation. You do a lot of calculus, which we are not going to do at this level. And so through the magic of calculus, we're going to look at some solutions. Now, in pre-AP, we looked at symbolic solutions. We're going to review those, so don't worry about it. We worked at a symbolic solution of depicting what Schrodinger's equation helped us determine about atoms. And this time, we're going to link those to going up one more level towards the actual solutions to Schrodinger's equations by linking what we call quantum numbers in with our symbolic representation. So that's where we're headed. And our goal is to find a region in space where we can find that elusive little electron. And we'll find that the best we're going to do is find a region in space where there's a 90% probability of finding an electron with a given energy. Will be the best we can do. Now, we have to represent that region in space, and to define a location, we're going to need at least 3 values. And normally it would be X, Y, and Z could define the location of an object. And we're going to use a relative scale, a relative internal scale to the atom. And we will need 3 quantum number, a 3-coordinate system. And so there's a minimum of 3 needed. And then we're going to get a bonus 4th piece of information that was provided by studying spectroscopy. Remember I said the interaction of electromagnetic radiation with matter is important, and it's broadly called spectroscopy. And so from some of that data, they discovered that 4th quantum number. So we're after 4 quantum numbers and their symbolic representations. So let's start with a little bit more about Schrodinger. The solutions to his equation are called wave functions. So a function that is based on wave mathematics. And we designate it by the Greek letter pi. Now, wave functions are called quantized. We've used that word a few times already. It means only discrete certain ones are allowed. So an electron, until it is free, electron does not have a continuum of energy states available to it. It only is allowed certain particular ones that are based upon the structure. So allowed, again, is that mathematical and physical feasibility. Physically, in terms of the structure of the atom, it just is not going to happen. And of course, since we're hoping our mathematics match that, it is not mathematically reasonable either. Now, Schrodinger's equation, the goal is to solve for the energy of an electron. So the best we can get is that probability information. Now, honestly, as you get to atoms or ions that are larger than, say, a helium +1, or maybe even a lithium +2, if you get into many electron situations, scientists have moved to much, much more complicated mathematical models to help understand the structure. But this is a great introduction to the use of models and how it's going to lead us to a way to depict the electrons that provides information of how they function and behave. So it's going to be a very, very useful model. But now they're going to use, scientists use very complicated computer type models for this. So the wave function squared is really what we're after. The wave function squared defines a region in space where there's a 90% probability of finding an electron with a specified energy. Unfortunately, now once we get to the full definition of this, the full definition of this is going to require 3 quantum numbers. And by the time we get to that, it's called an orbital. Now, if I was queen of the world, we would not call it orbital because that implies electrons orbit or move around the nucleus in some sort of circular pattern. And we're really, to the best of my knowledge, we really don't know how electrons move. Now, there may be some great research going on that is getting closer to that information, but we don't know that yet. So here's what's going to provide you with the success you need, not only on those AP and IB tests. Yes, those are important, but to me, there's even a greater value to this. These are going to help you, lead you to developing some of those critical thinking skills that will help you in any type of argumentation. Again, it's about making a claim and then providing evidence to substantiate that claim, just like what we do in our labs. And the claim is pretty easy for most people. But if you've listened to politicians lately, providing quality evidence to support their claim can be a challenge for some of them. So beyond science, I think that it helps with that. Certainly within science, it's going to provide you with a high level of critical thinking for your next level of chemistry and as college prep. And the key to that is you're going to have to justify. You will see that word so often on tests and in my activities. It will say, what happens if, or what will occur, and you're going to have to then provide justification. It will be followed by the phrase, justify your answer. Sometimes justify your answer with a calculation, and other times justify your answer with mathematics. And the key to the atom is to recognize that our justification has to involve electron-electron repulsion considerations and electron-proton attraction. So anything that we're going to talk about, any of the periodic trends that we'll ultimately get to, the models, it's all about minimizing the repulsion and maximizing the attraction. So electrons want to get as close to the nucleus as possible, but they still need their own little personal space away from one another. So we want to keep those 2 things in mind because that will be the key to our justification answer. All right? Not just an observation, it has to be a justification, a why statement. Why does this happen? Now, our principal quantum number is n. Principal, and this is where Bohr really helped us. Principal quantum number. We give it the symbol n. And the values that it can take on are integer values beginning at 1, not 0, but 1. So n can take on all integer values greater than or equal to 1. Called our principal quantum number. These are energy levels. You may see the term energy shell show up in different books. That's still a common term. I tend to use levels, but I want you to be familiar with that word. Now, there's 2 things that n provides us for. In terms of understanding the rough area of where we can find that elusive little electron. It indicates, in part, the energy of the electron. I would say it's the primary indicator of the energy, potential energy, and the distance of the electron from the nucleus. Now, as you increase energy, potential energy, that means it's further from the nucleus. It means it has the potential to get closer to form an attractive force between the 2. Now, I do want to give you a glimpse of the future here. I'm going to be honest, in terms of n, the energy is going to get a little mixed up as we apply these models to more atoms further along in the periodic table. And fortunately, the periodic table tells us exactly how they get mixed up. But the distance seems to stay true at least at the level of what we are going to be dealing with. But those energy levels will get mixed up a little bit. Now, the second quantum number will also provide a little teeny bit of information about energy, but it is primarily or principally going to be n that gives us that energy level. Now, each energy level, if we look at the number of electrons, each energy level can accommodate up to 2n squared electrons. Now we're going to find that each one has n squared orbitals. Since each orbital will hold 2 electrons, that means we get 2n squared. So if we're at the n equals 3 or third energy level, 3 squared is 9 times 2 is 18. So energy level 3 will be able to accommodate up to 18 electrons comfortably, meaning all of your attractive forces have been maximized and all of your repulsive forces have been minimized. That perfect balance between the two of those. Now, we're going to stop this video at this point so that we can keep a topic together on energy changes and calculating the energy within. We're going to spend quite a bit of time on the first quantum number, and then the other quantum numbers are a little simpler. There's no mathematics involved, but we want to get into the mathematics of our principal quantum number. So until the next video, signing off.